So my name is Irina Overeem. I'm with the Community Surface Dynamics Modeling System, CESDMS, at INSTAR at the University of Colorado Boulder. And I'm presenting some results that we did in a project that was funded from 2007 onwards by the National Oceanographic Partnership Program, and then separately by ONR for a graduate student extension. And the same student who did master's work there then applied for a fellowship to NASA and got NASA funding. So there's work from her that I'll highlight in this presentation. But so when we set out in this research on how changing sea ice affects the Arctic coast, this is, I think, Jessica doing, or can I make it a little bit bigger? Fit to page. Okay. We basically knew that sea ice minima were already on a declining pathway in like the early 2000s, especially, and that has only been corroborated over the last decade with a figure that you are all probably pretty familiar with, of like what the extent of the sea ice in the entire Arctic Ocean is. And there's a dotted line on here that shows how dramatic and low the sea ice year of 2012 was, and that we are pretty much on track, or in wintertime even worse, in 2016. So we'll see how that pans out over this summer until sort of the September time minimum. But in our group, we were focused on coastal processes, and we asked the question is like, okay, so this is maybe what is happening in the entire ocean, but what if we focus on like just the coastal region? Like, how has it changed there, and like how does that affect the system? And so the figure that's shown on the other side is, this is from the satellite data, the passive microwave data, that many people use as sort of the observational data set of over 35 years of sea ice concentration. And so we analyzed specifically the coastal regions in this data set, being careful for land contamination. And so some areas are not conducive to this analysis, but others seem to be good, and we validated it against higher resolution data for just 2 spots. So like there's some ground truthing that we did that has to confirm that the scale, even in a coastal region, is still accurate. But what we basically found is that there's, over this period of 1979 to 2012, almost all areas along the coast lost a lot of sea ice. And the way we express this is in open water days, and I'll use that throughout this talk, because that seemed a metric that is of importance of like a lot of the things that happen at the coast. Like coastal erosion that I'll be talking about, or perhaps it's like how much shipping can happen there. It could be like for ecologists, like how long the time is that polar bears spend on the land. So like the length of open water days is the period in time that at that coastal cell, like if this were one coastal cell, the water is ice-free. And so trends over the entire Arctic show that there's hotspot in that, like along the Beaufort Sea is a hotspot, not as much along the Mackenzie that always had like quite a bit of open water already. Disco Bay is another hotspot of change, and then around Svalbard, I think many people are familiar with that. Also the Laptev Sea. And some of those areas were known to geomorphologists as coastal processes changing there quite a bit too. And so what I'm putting up here is this came out in 2015, but a much earlier paper was done on just a single region by 2 USGS scientists who compared satellite data and topo maps from the 50s to like the early 80s to sort of like into the 2000s, and found this or the speed up of coastal erosion. And it kind of like fueled our curiosity because we knew sea ice was changing there too. And it kind of like makes you ask the question is like, how are those things related? And sure, there's two trends. They seem to be both accelerating, but what are the exact processes and can we like start modeling that? And so I want to talk today mostly on this erosion hotspot Drew Point where we did all our field observations, but I also wanted to make you aware that this same questions need to be asked for some of the barrier islands in this region where it's another erosion hotspot, and these barrier islands have been migrating inward or shoreward. But what I'll show you today is more typical to like sort of the bluff coast of northern Alaska. I know many of you are very familiar with that, but this is the permafrost style bluffs, and I have some photos to like show you. So they look something like this, where these are on high. There's also ones that are quite a bit smaller, like maybe two meters or so, but these are like 4 or 5 meters high. They have excess ice content, so they're like really ice rich, and there's a very shallow bathymetry going up to these bluffs, and you can see that they're like crumbling away. And this process of crumbling away actually has been happening already naturally, but what we've been seeing is a speed up of this process. So why would we be interested? Well, there's oil and gas infrastructure that was like really close to the coast. There's dew line sites that were like right on the coast. Then there's like a couple of like Alaskan villages that really need to deal with this and need to deal with the storm surges. And so I'll talk some about that. And I think there is an impact potentially on these offshore gravel islands that is like a bit more unasked question so far, or there's less that we've been doing on the modeling for that. So we asked, can we quantify the erosion processes, and also could we put these into models so that they are a bit more predictive as opposed to just correlative, and then are there any nonlinear feedbacks? And so ultimately our aim was to model the erosion processes to make predictions into the next 50 years or so. We went into the field to collect sort of a basic data set over 3 field seasons and patch together sort of data from the ocean domain as well as from the land on the permafrost temperatures and ice contents. We worked with the Naval Postgraduate School, Tim Stanton, to collect wave data and spectra. We collected some bathymetric lines and had like loggers in the water for sea surface temperature. And I wanted to point out, like here with this photo, that we were really interested in the really near shore data, and that's kind of like a spot where there's normally not as much data available because it's harder to get in there with boats. So like all our data collections were in 2 to 8 meters water depth, and like maximum about 10 kilometers offshore. So the very first year we immediately noticed that when the sea ice is near the coast, and that's what this period from day 1979 or like 179 to 91 illustrates, is that there is not much happening as long as the ice is there. And so there's really a protection and a boundary condition that's set by when the ice is there versus when the ice is not there. And we used time-lapse cameras to confirm this, as well as like measurements on the bluffs, and found like the erosion in this time early in the summer is about 1 centimeter a year when there's no access by waves yet. And then we found that like if we are if we're in warmer conditions and like the ocean can actually like interact with the coast, then the erosion is suddenly pretty rapid. And so like remember that I was saying that this is about 4 or 5 meter height. These blocks are typically like something like 15 meters long. And so in about 6 days of warm water conditions and not that much wave activity, this entire block has disappeared. And so we set up this iceberg melt model. And I see that the equation didn't quite correctly make it into the file conversion, but you can like look it back up, I think, in the original file. But basically what it sets up is a temperature differential between the permafrost bluffs and the seawater, and there's a wave height and period in there, and that quantifies the erosion. And so this very simple model seemed to work okay, but we were not sure that it captured everything we wanted. And what Jessica did is, and I welcome you to like look at these web links under like web links 2 to click on this like time-lapse camera. And I think if I do it here, it will like screw up the presentation, but it points to a YouTube video. I'm going to give you like a couple seconds to like pull it up. And so again, these blocks, so even if you're not putting it up right now, then what I wanted to like tell with this video is that within about 7 or 8 days, there's a block that's like 13 meters long and about 4.5 meters high, so like along this axis here and that length axis there, and it disappears completely. Like, and what you can also see is that yes, there was some wave activity and there was some time that the water level was a little bit higher, but it was definitely not as if the waves like totally topped these blocks. And what we were thinking is that this is basically a melt process. The ice content is so high that it's the warm water that baits these bluffs that rapidly gets rid of the ice that's in these bluffs. The other sediments are mostly peaty and silty, and so like the sediment just wafts away, and there's not that much of beach creation. A little bit, you can see this berm here. But so like not much feedback or protection that these bluffs help out with. And so then we set up the sort of the observations that we had. The iceberg model was created, and then we set up like, okay, what are the big boundary conditions? So we want to know where the sea ice is, and again, there's a link to the YouTube video that goes with this figure, where we were in Drew Point along the Beaufort is over here, and then Russia's over there, just to orient you. And then if you play that YouTube video, and I'll give people a second to pull it up. Can people see this, or if they click on those links?
Yeah.
Okay, great. So what you see there is that we use the sea ice concentration data to like define where the sea ice edge is, based on the 15% concentration that's traditionally used in sort of sea ice research to say this is the edge of the pack. We find that edge in all quadrants, but then we concurrently use the wind records from Barrow, and I think somebody introduced themselves from the Barrow Science Center. So it's the wind records from Barrow to define like what for that day is the dominant wind direction. And so you map the dominant wind direction, and that gives you like the distance to sea ice in the direction of the wind, or from the direction of the wind. And that gives you an idea of like what the fetch was, which then plugs into the wave model and into storm setup models. So there's this boundary conditions that comes from the sea ice concentration and the wind fields. And then with these, we used fairly simple 1D coastal profiles and used Army Corps of Engineers water level and wave models for shallow water waves and storm setup. This would not be as relevant if you're really in the deeper parts of bays where there's a lot of refraction happening, etc. But for the linear coast that we were looking at, the linear coast or the straight coastline, it seemed it was doing okay. And that's what these slides kind of illustrate, is that with a simple 1D model, we model both the setup of the water as well as the wave heights. And you can see that they match fairly well against the observed water level and wave height data. And so these were from buoys and from water pressure transducers, just for longer term water movement too. And then to put these things together, our student Katie Barnhart, she coded up a torque balance model which defines this coupled block. We used the code to erode, which was basically a temperature-based melt model, iceberg melt model, and then we drive this with the wave and setup of the water. And again, this is a little movie that you can see by clicking on that link of the Arctic coastal bluff erosion model. I know this model takes a little bit of patience, or at least in my realization, it does take a little bit of patience to watch what's going on. But basically, you can see there's a period of lower water level. A storm is moving through, but due to Ekman transport, the water's actually moved out, and the water's level is set down. And then so until here, later in August, there is a storm system that moves through that sets the water up. And then you can see that this block starts rapidly eroding over that period. And so this is calibrated, the settings of this are calibrated against that data that we had from the movie. So it's sort of the same temperatures of the permafrost. It's the water level is literally from the model and the water level that we had observed. And then the period that it takes to erode the block is fairly similar to the period that we saw these blocks disappear. So we were happy with yes, this is a crude approximation. We know it's not perfect. We know we might still be missing model components, like the sea surface temperature is difficult to do without a real circulation model. But at the first order, this really seemed to capture the processes. And then we put this into perspective of what if we would change these boundary conditions for longer periods. So over the 30 years that we have sea ice data, we knew that the number of open water days along that specific stretch near Drew Point had more than doubled. And that's what is shown here. Oh, I also wanted to grab your attention and say it's not that different if you look at different cells or cells that are directly near the coast or maybe one further into the sort of onto the shelf. So we were quite pleased with how robust the sea ice data seemed to be. But then if you plug that into the wave exposure and the storm setups, you can see that also over this period there's increases of cumulative wave height, which we kind of took as an integrator of the energy that's brought to the coast, and setups. And so Katie Barnhart actually ran this model for the last 30 years and found that the speed up of erosion is indeed seems to be following both the warming of the water as well as the increases of storm setup, or basically the cumulative water level. And that's probably something that Andre would be really interested in, because one thing that we did not incorporate here, we had tidal data, but we did not postulate a change in sea level. So definitely something that will add up to this problem, and we have not much data to control. What I wanted to bring this back to is, are there any dampening mechanisms to this? And so early on, we expected that, or we kind of thought that because the sea ice open water season expanded more in the fall than it did in the summer, and sea ice scientists had noted that for a while. So we thought okay, there's more storms that happen then too, thus we'll have more erosion in that time period. But what we actually found with the modeling is that these last, the expansion in the fall is not as efficient because the water is already really cold at that time of year. And so if there's less sea ice in November or so, and the waves can still attack the coast seriously, then still the erosional response in the sense of the bluffs melting is not as dramatic. So there's a little bit of dampening in that we think is happening. That being, and this slide shows the modeled largest erosion events, and it corroborates what we were just postulating. Whereas in this late period in the year, there's not many really high impact erosion events anymore, and it's basically because the temperature of the water is not cold enough to do a lot of or to provoke a lot of erosion. I want to make a note though that that's true for bluff erosion. Of course, there's still coastal flooding in that period, and water can be set up really high, and so it's not as if there's no impacts from these late fall storms. It's just that the bluff erosion is not as efficient that time of year. Definitely in the barrier settings, this is an important time of year, and this model would look different for sand transport than it does for the melt model. The last part of this study was to look at what the future of open water is. And so we went to the the community earth system model, and kind of took advantage of the large ensemble that's just been put up over the last 2 years, where there's 30 model simulations, or we use 30 model simulations. They are all identical except for round of errors in the very beginning in the boundary conditions. So it is a set of repeated models over and over again. And so what the climate scientists tell us is that captures natural variability, but it allowed us to look at what are averages in the number of open water days along the coast, and then since we were doing the analysis on a grid, we could do it for the entire grid. And so what this is illustrating is the number of open water days in 2000, where you can see that in many areas it's still only 60 to 90 days, especially in Baffin Bay and along the Beaufort and the Chukchi and the Russian coast. And then if you step to 2050, that's mightily changed. And so we can, based on the community earth system model, we can expect this vast expansion of the number of open water days. And if you look in this paper in Nature Climate Change, the other thing that the graduate student Katie Barnard did at the time was to look at when is the first day and when's the last day of open water, and sort of see that expansion in the seasons. And it's quite dramatic. And so this is the last animation to go with this talk, where we're looking at these averages of open water days in the 21st century. I'll pull it up myself. I think my screen just got taken over by a PowerPoint. So basically there's this dramatic expansion of Arctic open water. There is lingering ice that, especially in the Arctic, in the Canadian archipelago, but we can expect a quite a bit longer open water season along the Beaufort and the Chukchi based on these analysis. And so the data allows for picking any point at a 100-kilometer grid scale sort of. So like in regional, and you can like look at trends along the ocean, the Chukchi, and along the Beaufort towards the Mackenzie, for example. And Katie has done some of that analysis and presented it in the paper. So just to conclude, we found that erosion is really widespread. 84% of the Chukchi and Beaufort coasts see erosion nowadays. The average rate is about 1.7 meters for the Beaufort coast. It's a little less than the Chukchi because there's more gravel and even like some hard rock coast there. So like there's a difference between the Chukchi and the Beaufort. The extreme areas have more like 16 to 18 meters per year. So there in a few years you can have like as much erosion as like a football field. And so this is definitely something to like pay attention to in like infrastructure planning, etc. Over all these areas, wave exposure and storm surges have increased. But since we're finding that erosion of the icy bluffs is a thermal process, like seawater temperature dominates the rates as well. And then so far we still stick to our hypothesis that there is a dampening mechanism for these bluff coasts where it's melt dominated. That erosion there is less efficient in the fall season, but this is definitely something that does not apply to when you're looking at barrier islands and it's a sand transport dominated story. So what are our new challenges? I've always been interested in figuring out like the coast at the deltas, like the Yukon and the Mackenzie River, but also the smaller river systems contributing to the North Slope. So for example, the Colville. We know these river systems drain their freshet spring water onto sea ice that's still shore fast. And so that's really interesting to me because the water is relatively warm and it may have consequences for breakup dynamics. And so one next step of figuring out these coasts is to figure out what the deltaic parts or what the rivers are contributing to the story. Another question that we've asked is, in the Arctic sort of climate community, there's a work being done on Arctic cyclones and how they're changing into the future. And so we tied into their work and trying to figure out like what if these extreme events change, what if their wind directions change, and then we focus on storm surges that are setting up the water level high that's impactful, and a bit more on barrier and spit dynamics. And then lastly, and this is something that's being discussed quite a bit in the NASA Arctic Colors initiative, is like how coastal erosion impacts carbon and nutrient fluxes to the nearshore system, and that there's quite a bit of need for observations during the transition times. So like in the late fall when it's hard to get data, or in the spring season when the ice is still there, that's the time that we have these data to control our models so far. And that's about it. Thank you.
Thank you, Irina. That was a great presentation. A quick question, connecting both presentations, is there any engagement or are there any plans for engagement with FAMOS? Because the last slide has a number of thematic areas that are of interest to FAMOS, I think.
Yeah, yes, Mike invited me to FAMOS and I need to still sign up. And this question is basically something that Mike Steele and I have been interacting with, and we like put in a proposal to ONR earlier, but I mean, it's difficult to get funding for that close to the shore, and they were like on their budget, but so it's not been funded yet. But yes, we do have connections, and I think the connection to Mike there is good.
Awesome, thank you.
The second one on the storm surges is work that we're proposing to do together with Steve Vavras, who's at works on like sort of more the cyclone dynamics and the climate modeling parts.
Thank you. Are there any questions for Irina?
Irina, this is Andrei Pashutinsky. I have a question. How do you include tides? Are they directly included?
They have been directly included, but we do make an assumption that they're like similar at Prudhoe Bay, which is about 40 kilometers from our at test sites, and there's a little tide gauge there, and so we've been using that data to like drive the model. The tides are fairly or like they're like microtidal scale. But they are like in those wave and water level modelings, there's a tidal component there. I think what I'd be interested to hear your opinion about is how sea level change in this area is going to make a difference, since we found that water level is such an important constraint, and like if you set up the water by 20 centimeters, it makes a big difference. And I think that's, I mean, sea level change over 50 years is going to be probably quite a bit more than that.
Yes, in Alaska, there are two components of sea level rise. One is that land is going down, and second one is world ocean sea level goes up. So
right.
This is doubled factor.
Right. And so ideally there would be like efforts that model that locally as well, I think.
Yes.
Thank you. We have time for one more question. Or none? Okay, thank you so much, Irina. That was great.